Good morning. It is Saturday, October 19th, and I thought today I would talk a little bit about my time at the Kennedy Space Center for you today. I started working for Lockheed Space Operations Company on July 8th, 1985, as a young Space Shuttle main engine avionics engineer. The next week after I started working, the launch of Challenger and its mission 51F was scheduled. However, at T-minus 3 seconds, engine number 2 experienced a failure where, during the start sequence, the chamber coolant valve, which is supposed to close slightly because it directs how much coolant goes to the engine nozzle, it was a little sluggish, and it reported the failure and then switched over to the redundant channel, which was successful in closing the valve. However, the reported failure, or major component failure, MCF as we call it, caused Challenger's main onboard computers to shut down all 3 engines and cause a pad abort. The valve had been successfully opened at T-minus 4 minutes when we went into the final purge sequence of the 3 main engines without any issue. So it turned out that this was due to hydraulic silting, and with the entire eyes of the Space Shuttle project and the program on the engine that I was starting to work on, it was kind of an exciting time. We rectified that issue by cycling the valve more often during pad testing prior to launch, and that seemed to fix that problem. And by the end of the month, Challenger was ready to launch again. It was an exciting time as a young engineer. This time, July 29th, 1985 at 5 p.m., Challenger successfully launched on its way to orbit with Spacelab 2 in its payload bay. This was a mission for microgravity research and also for Coke and Pepsi to try out different ways of getting soda to astronauts in space. So what happened, though, even though the launch was successful, at about T plus 5 minutes and 43 seconds, I think, during the ascent, engine 1, which is the center engine, one of the high-pressure fuel turbopump temperature sensors had failed off-scale high during the ascent. And at that time, 5 minutes and 43 seconds into the flight, the second and last remaining temperature sensor on the fuel turbopump failed off-scale high. But it did so in a way that while it was going from reading normal to reading off-scale high, it lingered above the red line limit, voting for shutdown, but still qualified. And it did that for 60 milliseconds, which is 3 strikes. And when the 3 strikes happened, the main engine computer on the engine shut engine 1 down. This caused the ground systems to recommend that the crew select abort to orbit, or ATO. Now, fortunately, Challenger had enough velocity to reach a stable orbit by burning the remaining 2 engines much longer. And so instead of a normal 8 minutes to ascent orbit, I think it was 9 or almost 10 minutes of burn to get to an orbit that ended up being 50 to 100 miles lower, but still stable. And they didn't care because they weren't meeting anyone. They were just wanted to be in orbit to do microgravity research. So for this particular case, the mission was successful and it completed all of its mission objectives in that lower orbit. However, the excitement wasn't over. Before it got to MECO, main engine cutoff, engine 2 had a temperature sensor that failed off-scale high. And so it was a little tense in mission control. And so the booster officer at mission control told the crew to take the engine limit control switch from auto to inhibit, to prevent the engines from automatically shutting themselves off, until Challenger was able to make a safe orbit on only a single remaining engine. Once they had enough velocity to make orbit on a single engine, they took that switch back to auto so that if something really bad happened, they would be safe. The engine would shut down and they would still be able to make orbit. So many years later, I was at a meeting that was very emotional at the Marshall Space Flight Center in Huntsville, Alabama, where the flight crew, that obviously have a vested interest, they're sitting in this thing, mission operations director at the booster console, the flight directors, and the engine project all discussed the use of the limit control switch between auto and inhibit. You don't want an engine to blow up, and that's why auto is a safety function to prevent the engine from shutting down, from going catastrophic and losing the crew and everything. However, there are times when it is really, if you lost an engine right off the pad, you would have to do a risky return to launch site abort, which has never been tested and most of the time was successful in the lab in the simulator. It had to do a powered pitch around, which we're not really sure whether the forces would be too strong on the orbiter in that configuration. So fortunately, we never had to experience that or test that. So it's a very tricky situation. You want to be safe, but there's some operation issues where you want to be able to manage the risk. How much risk do you want to take at different times? And so it's a very, very difficult discussion. And we never had like options of, well, maybe you could throttle the engine down and still provide some thrust in this degraded state. That's a very difficult problem to solve. And with the computers we had and the software available, it was not solvable during the shuttle program, unfortunately. But those are things, if you're building engines and rocket ships in the future, you want to look at your options. You want to thrust the engines at full thrust to provide as much force as possible. But there are other options to shutting an engine down. Sometimes you can reduce the thrust and it'd be a much more benign, safer environment depending on the nature of the failure. So anyway, that was some of my experiences back from 1985. And if folks like this, I can do other stories from my past and times at NASA periodically. So let me know what you think and if this was something you want to see more of. So anyway, hope you all have a great day. Talk to you later.